All right, let's talk about Kepler's laws. Kepler's laws are 3 laws that we use to describe planetary motion. But it really works for any kind of orbits, really. So the first law is called the law of orbits. And it says that all planets move in elliptical orbits with the sun at one of the foci. So I kind of tried to draw this and it got a little confusing. I have to explain a couple things here. So an ellipse always has 2 foci. We've got one here and one here. The sun is at one of those places. Okay, I've drawn it over here. We're going to say that it has a mass of capital M, and we've got this planet orbiting it in an ellipse with a mass of lowercase m. R is the distance from the sun to the planet at any given moment, and we're calling this theta. So this is the angle that the line between the Earth, or sorry, not the Earth, any planet and the sun makes with the x-axis. We've got a bunch of letters all over the place. A is called the semi-major axis. You know what? I should write that down, shouldn't I? Okay. A is called the semi-major axis. And it's basically, you could think of it as the radius of this ellipse at its longest, okay? So not the short way, but the long way, okay? Then we have the distance from the center to one focus is EA, where E is called eccentricity. I always spell this wrong. Eccentricity, where eccentricity is always some number between 0 and 1. I guess it could be equal to. So when eccentricity is 0, what we're saying is the distance from the center to the focus is 0 times A, so 0. That means the focus is at the middle. Basically, that means both foci are in the middle, and what you have is a circle. Okay, so if E were to equal 0, then that would be a circle. Notice if eccentricity was 1, you would have that the focus was way on the edge. You wouldn't have an ellipse anymore. What you'd have is like a line between 2 foci. You'd have a line. So I don't really think we call that an ellipse anymore. So really this shouldn't be or equal to 1. It should be like this. Okay. There we go. Let's see, what else do we need to know? Okay, these purple things, this is RP and RA. Let's write those down too. Okay. RP is the distance from the sun to the planet at its smallest distance is called perihelion. Perihelion. Okay, shortest distance. Basically, that happens once a year for a planet. Okay? Whereas RA, notice that is the longest distance when the mass is way over here, when the planet is way over here. That's as far away as you can get. Okay? That's called aphelion. I think. Let me check that. Alright, I went on like dictionary.com to make sure I was saying it right. Aphelion. I'm saying it right. Okay. Okay, that's the largest distance that you get from the sun. And again, happens once a year for the Earth. Once every cycle it happens. Okie dokie. Now most planets in our solar system don't look like this. They do orbit in ellipses, but if you draw it to scale, it looks almost like a circle. In fact, the eccentricity of Earth's orbit is only 0.0167. It's almost a circle. Not quite, but almost. Okay, so one more time, Kepler's first law, the law of orbit, says that all planets move in elliptical orbits with the sun at one focus. Alrighty. The next law is a little weird. I gotta explain it. The next law is called the law of orbits. I just said law of orbits. This is the law of areas. Ugh. Okay. I'm going to try and explain this conceptually first. Okay. The law of orbits says a line that connects the sun and the planet, so this blue line right here, okay, it sweeps out an equal area in the plane of the orbit in equal time intervals. So what I mean by that is, if I were to sketch this ellipse again, and I'm just going to really sketch it, it's like whoosh. Oh, that's really, really nasty. Okay, here's the sun. And if we were to say, okay, I'm going to have the mass, if it moves from here to here, 1, 2, in, let's say, you know what, this is not a planet in our solar system. Let's just say it's some time interval t. Okay, let's say 5 seconds or something. So in a time of t, the planet moves from here to here. What I'm saying is this area from right here to right here, this area, okay, would be equal to another area anywhere else in the orbit that's swept out by time t. So, for instance, over here, let's say the planet moves from here to here in a time of t. Also t, okay, also in a time of t, then it would be this area. What I'm saying is these two areas are the same, okay? That requires that over here, the planet be moving faster, because it's going over a longer arc length. Let's see. From here to here, it's traveling all this way in a time t, whereas over here, it's traveling only this far in time t. I need that to be true because since this one is closer, it's like, you know, area's length times width. Well, this one, the width is smaller, so I need to be more this way. Whereas this one, the length is much longer, so I need less up and down. So in a time t, they sweep out the same area. Okay? I know that sounds kind of weird, like that can't be true, but it totally is. In fact, we can prove this by using the conservation of angular momentum. Alright, so we're going to have to do a little math here, and I'm running out of room. So let's not do the math. Instead, let's talk about it qualitatively again, but this time with momentum. If you think about this, remember that the angular momentum of a particle, and that's what we're looking at here with m, the angular momentum of a particle is basically, well, it's I omega for anything. I for a particle is mr squared, okay, and I still got my omega. Omega I can put as v over r, mr squared v over r. Meh, meh. Okay, so in the end, for any particle, just a particle, one little particle, it's the mass of the particle times the velocity of the particle times the radius from the center. Okay, so think about it over here. Okay, and remember, angular momentum is conserved pretty much under a lot of circumstances. So over here, I've got a really long r, okay? There's my r right there. Mass doesn't change. So way over here, what I've got going on is L is m with a big R, so I'm going to have a little v, okay? Right here. On this side, R is a lot smaller. So L has to be the same size. M has to be the same size, but R just got small. Tiny r, which means V has to get a lot bigger. Okay, so when you're far away from the sun, your velocity is small. When you're close to the sun, the velocity is big. And those tend to even out. So if you do this sweepy thing with the same amount of time, this small velocity sweeps out less arc length, I'm just going to draw all over this. But to get area, you do basically, it's kind of like a triangle where this is one side of the triangle and this is another side, the R. So the small this side is canceled out by the large this side. Where over here, the small this side is canceled out by a big this side. Okay, and they cancel out in the end. But remember this is important. Okay. Oh, we're getting long video here. Okay, last law. Last law, law number 3. Law number 3. Okay. Law number 3 is called the law of periods. This is my favorite. I like this one. I think it's pretty cool. And it's actually not that hard to prove, okay? Number 3, law of periods. Now you did this one on your lab. That you did. Okay. So let's think about, to make this easier, let's think about a circular orbit. So I'm going to put my sun in the middle, right in the middle. And it has a mass capital M. Alrighty. And I've got this planet. I'm going to try and draw a circle. It's not going to look great, so I'm freehanding it. Pretend this is a circle. Alright. And I got my mass over here somewhere. Let's put it here. Right there. Little mass. Little mass. Okay. If this is moving in a circle, it needs to have a centripetal force. Okay? And it needs to have a centripetal acceleration. Basically, this thing has a constant velocity going around the edge, but it needs some sort of acceleration toward the center, centripetal acceleration, which we know 2 ways to write that. We could do v squared over r, or we could do omega squared times r. Those are both completely valid. They're just putting in omega equals v over r, like, as, yeah, anyways. Okay. I'd also like to point out, just because it will come up later, that period is the time it takes to go around once, time for 1 revolution. 1 revolution. Okay, because that's going to come up. And the circumference of 1 revolution, so this distance all the way around, is 2 pi r, because that is the circumference of a circle. Okay. Now, if you were to draw a free body diagram of this, our little planet mass here, okay, I'm going to try and draw it the same as it looks over here. There's only one force acting on it. Just one force. Force of gravity. Alrighty. So if I were to do Newton's second law for this thing, well, F net equals ma. The only force is the force of gravity, so that becomes my F net. Just leave it. Alright. My mass is mass. And the acceleration of this thing is not 0 because it is accelerating. The acceleration is the centripetal acceleration. So v squared over r. Alright? Now the force of gravity is not mgh or mg or something, because we're not dealing with stuff close to the surface of the Earth. We're dealing with the force between 2 masses. And the force between 2 masses is g, m1, m2, so I've got big M and little m divided by the distance between them squared. Okay, keep this side the same. Well, I'm actually going to, yeah. Okay. Notice one of those r's goes away, so what I really have is g times big M, little m. Oh wait, m's go away too. Goodbye, 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 goodbye. So what I would end up is gm over r equals v squared. Alrighty, that's all well and good. But v, velocity, for any velocity, if you've got a constant velocity, is distance over time. For going around the circle, I know the distance for an entire circle is 2 pi r. And the time for an entire circle is period, or capital T. So I can put this over in here. So now I've got, and I'm going to change colors because I got to scooch back up the page here. Okay, so now what I've got is GM over R equals 2 pi r over t squared. So if I square everything, I'm just going to square everything right off the bat. I get 4 pi squared r squared over t squared. All right. Now I'm going to clean it up a little bit so that I get period equals something. All right, so if I do some rearranging and algebra and stuff, let's see, multiply both sides by t squared, I end up with t squared equals 4 pi squared over g big M all times r cubed. I'm going to put parentheses in here. Oh, no, I'm not. Okay, just because I ran out of room. Okay, so this actually right here is the law of periods. The law of periods says that the square of the period for, well, anything, it doesn't even have to be a circular orbit, the square of the period of any planet is proportional to the cube of the semi-major axis. So for a circle, the semi-major axis is just r. If this was an ellipse, we would just change that r to the a. Okay, this the long one. Okay. Now we just said proportional, where proportional just means it's multiplied by some constant, because if you look, all these are constants. 4, pi, g, big M, those are all constants. Also notice, there's no little m in here. So it doesn't actually matter what the planet is. It only matters what the planet is orbiting. That can come in handy, because you can use this backwards, where you could measure the period it takes for something to go around the sun and measure how far away it is, which is completely doable, all of it doable with telescopes and like a timer. And you could solve for the mass of the thing in the middle. That's in fact how we know what the mass of the sun is. We've just looked at how the planets go. This also means that for multiple things orbiting the same object, such as all the planets orbiting the sun, you can compare those planets to each other, since it doesn't matter what the planets are, all it matters is that you're orbiting the sun. Okay, let's see, what can we do with this? Well, nothing, because this video is coming up on 18 minutes long. I think that's plenty. Let's stop.